Okay. All right, so you may refer to the formulas over here. Yeah. Okay, so let's continue to our chapter 3 here. Okay, I believe you guys have already seen or studied this so-called the conditional probability. Okay, so I'm not going to look at this thing. I mean, straight to the point, just look at the definition and the math part for here. Okay, so first of all, the definitions. So as usual, if we have a probability space omega script fp, so and a, let's say first of all, b is a fixed event, okay, which is a with non-zero probability. So the conditional probability of a given b is like this: pa and b over pb. So you should have already seen this from definition before. Okay, in your undergraduate course. Right, we do these things. Okay, when PB equals 0, we just simply take PA given B is equal to PB. Okay, so this is 0. Okay, so the conditional probability, I think this one is correct. So the next one is actually given in these theorems. Okay, so we have these theorems. So if we define P, okay, let's say B is an event with non-zero probability, then we define PB to be like this. Then we can show that PB must be a probability on this sample space. Okay, let's look at the proof for this part. Okay, so theorems. So this is theorem 3.4.4. Okay, so if given B is an event and P of B is positive, so if we define PB of anything will be P of this. Okay. So then we want to show this PB is a probability measure. So let's look at the proof for it. So we have to verify this PB satisfies the three conditions there. Okay. So we can see that we can verify one by one. So PB is a probability measure on this omega together with this script f. So because it satisfies these three. Okay, we do one by one. So the first one, we need to prove this. PB of omega must be 1. Huh? Okay, I think that's right. So PB of omega. So we can see this is a PB according to the definitions omega B. So by the definition of this, so that will be omega and B over PB. So this clearly, which is equals to PB over PB. So this is equals to 1. So that's why we get it. So P of omega is equals to 1. So this is the first condition that we want it to be satisfied. So the second one, Okay, second one, what we want to prove is we want to show this if AC belongs to F, A. So if A is an event, so B of A must be non non-negative. I think this is clear, so we can verify it directly. So for any event A, so you can see PB of A. So this one directly, according to the definition, will be A and B over B. So I think it's clearly, so this is greater or equal to 0, clearly. So we look at the third one. So we consider a disjoint sequence of events A1, A2, A3, and so on. Okay, so I have to be disjoint, okay, and event. So then we carry on the calculation. So PB union of all the AK. So again, by the definition, so this is the union of all the AK given B. So this is given. Okay, so K running from 1 to infinity. And we following the distributive law, so that this becomes a P of union of all the A n over this. Again, K is running from 1 to infinity. Okay, now because of all the AK are disjoint, okay, then we know AK over PK are disjoint. So this is because AK are disjoint. Okay, it's clear. When this is disjoint and P is a probability, this thing must be like this. So we can actually write this as a summation of a PA and AK and B running K running from 1 to infinity. But the definitions, according to the definition, the one inside here will be P AK given B. So then this will becomes. So this one, by using the definition, so this will be like this. All right, so done. So this is actually what we want to do. That is, we consider for disjoint sequence events A1, A2, A3, and so on. Then we can have these conclusions. PB of this equals to this. So this is actually our third action for a function to be a probability. So then we come back to here one by one. So number one, PB omega is equals to 1. Okay. Number two, you can see whenever A is an event, so PBA always greater than 0. So this is the keywords in the second actions. And a keyword for the third action will be for destroyed sequence of event AK, then PB of union of AK, K running from 1 to infinity, must be equals to the summating of PB AK. So once we have verified that PB satisfies these three conditions, then we can have conclusions that PB must be a probability measure on omega. So this is how we can prove the theorems 3.4.3. So, and the next one will be these theorems. Okay, the next theorem will be the theorem of total probability. So, so this is actually an intermediate step for us to construct the Bayes theorems. Okay. So let's look at it. So if we have a B1, B2, B3 is a partition of omega. So that means all these B, K are destroyed and the union of them equals to omega. So then for any event A, we're going to have this formula. All right, so let's look at the proof for it, or look at the statement first. Okay, so please consider this. Suppose B1, B2, B3, and so on is, it's that form a partition. Okay. So when we said it's form a partition, what does it mean? So this one simply means that first of all this must be destroyed whenever I not equals to j. Okay, and secondly, you combine all the b, it end up to be our omega. So that's the meaning of all these b form of partitions for omega. Okay, suppose this is for omega, and for any event A, so we have this formula. dA must be the summating K running from 1 to infinity. Yes. So actually, proof is not difficult. So we just make use of these definitions as well as this formula here. Okay. Okay, maybe we begin with the right-hand side. That will be easiest. Okay, so this is the case. Okay, next by the definition of this, so this can be written as PA and B and over PB and BB, right? So you can see these two can be cancelled off. Then we have summating. Yes. Okay, so we have a same argument. According to this, all the pk are disjoint. When all the pk are disjoint, so this must be also disjoint. So we have this. We have a similar argument, so we know pk are disjoint. So A and pk also disjoint. So when this is disjoint, then we can have this. So the summations it becomes this. So this is actually same as the previous proof. Then we can put this one as summating PA union, not union, intersect with all the union of all the BK. And also, according to our hypothesis, we have this one. The union of all the BI equals to omega. Okay. Here again, so this is the case. The union of all the BI is equals to omega. So that means this one will become summating of PA and omega. So I think it's clear. So, oh, sorry, no more summation here. Okay, this one, no more summation here. No summations here. So, and then, so then P and, so this must be PA. So this is equals to the left-hand side. So done. That's the formula. You can get it. So it's a good exercise or a good example to demonstrate how we apply the formula in probability in doing some sort of the derivations of it like that. Okay, next, last theorems will be this. So this is one of the important formula in probability theory, the Bayes theorems. Okay, again, let's say all these BI form of partitions for omega. Okay, and if A is any event, so we can have this relationship. So which is actually can get it from here. So you can look at this part. So we can actually, this one, right? We can directly substitute into here to become our PA into this formula here. Okay, so let's come back to this. So this is the Bayes formula. Okay, again, we must have a hypothesis. So we suppose V1, V2, V3, all this form a partitions for omega. Okay, so from our previous theorems, then we have this. P of A is equals to mating of K equals to 1 to infinity, P A and B, P given B, and then multiplying PB. Okay.
Given PK 嘛，所以你 multiple。
So this is the formula that we have proven just now. So this is a partition away. Okay, now again we consider any event A. So we look at it. We look at the right hand side, same of it. So that is equals to P A B I P B I Actually, maybe I change the color so just to highlight this part for you guys. So you look at this formula. So this is our previous theorem, the theorem so 3.4.4. Okay. PA can be expressed in this. So that means this is actually our PA, right? So then we can put it as this is okay. Then this part. Maybe I highlighted this one with green color so you can see how the things evolve. So the green color part, by using the definition, can be put as PA and BI over PBI, right? So then I'm going to have a PBI over here, remain the same. So for the red color portions, that will be actually our PA. So then we have our PA here. Then we can cancel these two. So the remaining will be just equals to P B I and A. So this we can sort A and BI, BA. So I think this is clear. Then this will become PBI over A. So that is your left hand side. That's it. Okay, so this is what we so-called our Bayes formula. Okay, we look at a special case whereby we only have two partitions, okay, B and compare B. So how the formula looks like. So we look at a special case. Or the simplest case, okay? So let's say we take B1 to be B and only two of them. B2 to be the complement of B. That's it. So the remaining are empty set. So if we put into our formula, then you can see that it becomes like that. P of B over A okay, is equals to P of A over B, PB So multiplying PB, so the whole thing divided by, I'm going to have a P of AB plus another one. So that is this is B1. This is supposed to be B1. The next one supposed to be B2. Okay, so this is supposed to be our B2. So then it would be PA given the complement of B, then P of complement of B. So this is a special case or the simplest case. Yeah, if we consider two partition B and the complement B, so then we have this formula over here. Okay, so if you look at it, so usually this one, which is so-called the prior probability. So, and this is known as the posterior probability. And this one, usually, this is the probability, how should I say? This one should be the, I mean, maybe I will say this is the probability from the data. Okay, probability based on the observed data. Okay, based on the observed data. So in most of time, so this posterior probability will be the probability that we want to determine. So this is something that we want to determine. And this is the probability that based on the observed data. So that means this is, we can actually get it from the from the data or from the experiment. Whereas this prior probability is something that we don't know. So this one, something, this is the something that we don't know. Uncertain, or we can say this is the uncertain. This is uncertain. So that's why this is the part, the red color one is uncertain. So is the one we put in our hypothesis, and then we calculate what is the posterior probability that we can have. So okay, forget about examples. I think you should be able to get a lot of article or video in YouTube regarding to the implementation of the Bayes theorems. So maybe you can refer to the YouTube. Okay. So browse the implementations. I think there should be a lot of video in here, Bayes theorem in YouTube. Okay. For the implementations of it. So roughly speaking will be something like this. This is a property on positive term. Okay, maybe one we can put it in a simple examples like that. So for example, in current time, so for example, so we can have this this A and B, and B. PB is the prior probability. Okay, so PB is a prior probability. Okay, so for example, if you can see the events A to be someone, okay, let's say someone do a swab test for COVID. Okay, let's say someone with COVID test. Okay, someone do a COVID test, and then the result is positive. Okay, so someone do this, results positive, and let's say B. So this is the chances, or the chances percentage for someone to be affected COVID. Just for examples. So this is something that we don't know. We don't know, but what we can. This is actually uncertain, right? So this one is a question mark. We don't know. But what we can do is we can roughly put it this way. So we can base on the we can base on the total cases, okay, divided by the total populations, okay. So then we can get sort of a rough idea the percentage for someone to be affected by this COVID, okay. So that means this one we can actually sort of like we can get it. So at least we have some idea for it. So however, this is also uncertain. We can also based on something that you can get it. So then you can look at this. What is this PAB? Then you can see this PAB. So this is someone tested. So that means this is the probability for the person affected already. Affected COVID. Confirm and one more. Tested positive. Okay. Even that, and in fact, he or she is already affected. COVID. So that's a probability. So that means, in fact, the person is really got affected by COVID, and the result tested is positive. So that means the result is true. So how about the other one? So A, not B. So that means this is the one. So this one, the result is positive. But in fact, the person does not affected. So that means the tested result is not true. Okay, by COVID. So this is the case of it. So all this we can confirm later. Okay, this one can be how should I say? This one we can know the value for the probability based on the data, right? So then we can all putting inside here to calculate this probability. That is, what is the probability that someone, the test result show positive is true? So we can use it to do this testing. Okay. So how is the probability? How reliability for the swab test? So this we can use this formula to test for the reliability for the test kit. Okay. So and this is actually this green color is something that it can be measured by the data or the observation data. Okay, we can observe this. However, the only issue will be this PB, this prior probability. Prior means is something that is before happened. Okay, so we don't know. This is something uncertain. So that's why this is an unknown parameter that for us to set it inside. So this is how we are going to apply this Bayes' theorem. Okay, but anyway, sorry, I am not really this kind of applied field. Okay, I will more focus on the theoretical part. Okay, so I think you can, if you are interested on this thing, you can go and Google it. Okay, you should able to get a lots of interesting video explanation, which is much better than me. Okay, so you can refer to it, right? But anyway, I will focus more on the theory part, okay, how to derive this formula, how to apply the property for the action of the probability measure, and then to derive the formula. Okay. All right. So that's the end for chapter 3. Okay, great. We have about 40 minutes left. Okay. Before we continue to the next chapter, so you have any questions? Okay, I suppose no, right? Okay, so I think let's proceed to chapter 4. Okay, chapter 4 is about the expectation or the expected value or the average for random variable. So again, this is something that you should have already learned in your undergraduate courses. Again, I always suppose you have seen this before. Okay. So let's look at here. This is something that you have learned, okay, about expectations. Or EX, okay. So what are they? Okay, one by one. First, so I think this is something well known. Okay. So first of all, let's say X is discrete. Okay, X is a discrete random variable, and the image of X is actually, okay, make it easy. The set of all, okay, maybe the image of X is this, is a discrete value, 0, 1, okay, maybe 1, 2, 3. 1, 2, 3, 4, 5, and so on. Okay. And supposing the probability mass function will be P of X equals to K, right? Then you have this. Then we can have the expectation value of X. So it can be calculated by using this formula. K equals to 1 to infinity. So we are in from X, P, X equals to X. Okay, I think you have learned this in undergraduate courses. So this is the case whereby when we have a discrete case, so this will be the formula. Discrete case, then this is the formula. Okay, just the relations. Okay, likewise, maybe this is A and B. And let's say if G is a Borel function, okay? And G is a Borel function. In a way, you can say G is a, which means G is a random variable on R. You can put it this way. Okay. If G is a Borel function, then we can actually calculate. G is a Borel function, so this will imply that G of X also a random variable on omega. Okay, we have this. So then we can talk about the expectations of Gx. So that means in this case, then we're going to have E of Gx will be equals to, what we need to do is we just replace this X equals to 1 to infinity G of X, P of X equals to X.
Okay.
So I suppose you should have already seen this formula, and you already know how to, you have already applied this formula to do all sort of the calculations. Okay. So this is the well-known formula for discrete random variables. Okay, the formula, or you can say the definition for expectations for X will be this. And if we have a Borel functions G, so the expectation value for Gx will be given by this. Okay? So we just need to replace this X with Gx. Huh? So this is for formula for our discrete case. Okay. What happens if we have another one? So supposing X is absolutely continuous. X is a absolutely continuous random variable. Okay.
Sorry, doctor.
Yep.
I want to check, right? Is Borel set the same thing as Borel function?
Come again?
Is Borel set the same thing as Borel function?
Oh, no. One is function, one is set. You put it this way, okay? You put it this way. You can put this as an analogy. So Borel set. Okay, I think you put this. How about I put it on top here? Better. Okay, good. I think it's good. I think I just give you a better idea. Okay, it should be like this. Borel set, right, means event for omega equals to R. You can put it this way, something like that. So Borel set is an event, got it? Borel set is an event. So when you said Borel function, maybe I hate this, man. Okay, so this might not be so precise, okay, but the idea is like that. So when you talk about Borel functions, okay, so the analogy will be, so it will be a random variable for the case when omega is r. You can put it that way. I hope this is clear. So if I use the terminology events and random variable should be better, right? Okay. So the reason that I mentioned Borel function is I want to emphasize. I just want to emphasize when we said Borel's functions. Okay, I just want to emphasize that this omega is r. Okay, when we talk about Borel here, so the omega is r. This is something that we want to emphasize. Okay, just like that. So it's here. Gx is also n. All right. So because when we consider the original case, x might not be a random variable on R. So the sample space omega could be something else. Oh, I hope that's clear. Okay, maybe, sorry, I better go up, let you have a look once again. So you may put it this way. Borel set means in red. When omega is R or omega is a subset of R, you may put it like that. Borel function means a random variable when omega is R or omega is a subset of R. So I hope it's clear. Okay, so let's carry on. So first, this is the story about how we're going to compute the mean or the expected value for discrete random variables. Okay, we are using this formula. So when we come to an absolutely continuous random variable, so we have a similar formula. Okay, so then we have to refer to this one with density functions f, let's say fx. So the formula will be quite similar. I think you guys already know when we change from discrete to continuous, what we need to do is we just replace the summation with the integral sign, right? And replace the mass function with the density functions, right? So when A is an absolutely continuous random variable with probability density function fx, so then we are using this for exob, we integrating r x f of dx. Okay, like I said, we just need to replace the summations by this integral. Likewise, if we have this, if g is a Borel function, okay, so g is a Borel function, so this simply implies then g of x is also a random variable on omega. So that's why we can next time we talk about this. Then we can have our e of gx is given by this formula, e of x multiplying f of x dx. So another two formula here. So again, I believe you already familiar with this formula. You have already applied this formula to do several calculations already. Okay. So I think this four formula already enough for you guys to solve most of the practical problem. Yeah, because in practical, most of the random variable that you have faced will be discrete or observably continuous. You don't have the other one. Okay, and also you can apply this formula to do the calculations. Okay, but when we come to theory, so for practical, this is already enough. Okay, for practical, these formulas already enough to solve the problem. Most of the problem, I would say, the problems. Okay, so however, for theory, we always want to look for a single, just one formula, okay, or I rather say formulations to discuss or to describe, or maybe you said to describe EX. So that is the things, right? Okay. So that's why in theory we always want to unite all the formula. So instead of every time we have to see discrete case or continuous case. Discrete, okay. Then discrete case we use this formula. For continuous case, we use another formula. Okay. So that's the thing. However, when we come to theory, we always look for it. Since this formula, I'm talking about this, okay, this one, since this formula and this formula describe the same concept, that is the mean or the expectation value for the random variable. So in theory, we always want to look for one single formula to describe it, or we want to unite these two formulas into one single formula. Okay, so this is what we want to discuss in our course here. Okay, so that's why in this chapter or those we discuss this expectation value once again, which you have learned it in your undergraduate courses. That four formulas is already enough to solve most of the things. Okay, however, in this chapter, we want to discuss how to describe this expectation value with only one single formulations. Okay, and after that, we want to see under different situations or different random, how this formula can be split into different formula. Okay, so this is what we want to discuss. All right. Okay, so this is the thing for it. Okay, next will be here. Other than that, we want this, just to recall. So we want the EX to have these properties. Okay, and we want this to have this property. Number one, if we have indicator functions, so the expectation value for indicator functions must be equal to the probability of that event. And secondly, we also want this. When X is a positive or non-negative random variable, so we're going to expect the expectation value must be also non-negative. And number three, we expect this X plus Y must be equal to EX plus EY. And also, we will also expect this E of a constant, let's say C multiply X must be equal to C dx. Right. So if you use these two formula, okay, if you are using either this formula, the formula for a discrete random variable, or if you use this formula, the expectation value for continuous random variable, so you can easily verify that your expectation value will fulfill all these properties. Yeah, easily. So now we want to have a single formulation or one single definition for Ex such that it also fulfill all these properties. Okay, so this is, you can see, we will slowly establish these formulations, okay, to do this. So that's the maybe the at least let you know the main intention for these chapters and what we're going to do for this chapter. Okay, so that's why you can see the difference between this the content in this course with what you have learned in your undergraduate course. Okay, okay, so how to define this Ex? All right, so we split into 3 stages. So stage number 1, so we look at simple stage 1, we consider simple random variable. Okay, and then we consider simple random variable, and then we construct or we define what is the expectation value. Okay, so that is stage 1. And then stage 2, we look for the positive random variable. Okay, we see how to define expectation value for simple random variable. And next, we see how to define expectation value for positive or non-negative random variable. And finally, we come to a stage 3. So how to define an expectation value for any kind of random variable. Okay, so that is our stage, one by one. So I hope you can follow the flow for this chapter. All right, so let's whether we follow this. Okay, I will stick to the point. Okay. Okay, now I'll stick to the point. So as I said, so stage 1, 2, 3. So let's begin with stage 1. What if we have a simple random variable? How to define the expectation value? Okay, so this is a simple case. First of all, what is meant by simple random variable? I think we have discussed already in chapter 2. So simple random variable, okay, here, maybe just a remark, okay. And here, I just want to, here, I try to use a S, T, and so on. So this one to stand for simple random variable. Okay, I try to distinguish, yeah, ST. Yeah, try, and then I try to reserve X, Y, Z, all this for arbitrary, any kind of random variable. Okay, so that when I put S, okay, at least you have some idea. Or talking about simple random. When I put X, or then I want you to immediately link of this, or this X might not be is not a simple random variable. All right, I try to do it in this way. Okay. Okay, what is a simple random variable? We have discussed this in chapter 2. A simple random variable S is a random variable which takes a finite numbers of values on it. Yeah. And we can always write a simple random variable as a linear combination in this form. Yeah. So in particular, we always assume A1 up to AK to be partitions for omega. Okay. So I think you know the meaning partition. Again, partition means they are disjoint. And firstly, they are disjoint. Secondly, if you are taking union of them, you combining all of them, it will be equals to omega. Right, so this is the simple random variable. S will be summation of this. Okay, next. Okay, so this is the definitions. This is very important. We always assume AK to be disjoint, no overlapping. So in this case, then we can construct. Okay, maybe I shall put it over here. For a simple random variable, S is equals to summating. Take notes here. When we say simple random variable, so the image for this random variable always finite. Okay, so that means here cannot be infinity. Yeah? Okay, it must be some integer. Okay, for simple random variable, we can write this. And I want to take notes here. Here, A1, A2 up to AK form a partition for omega. Okay, so I believe now you notice the meaning of partition. There are two properties. First, they must be disjoint. Secondly, the union of them will be omega. All right, so for a simple random variable, A is equal to this. So we just simply define E of X to be, E of S. If S is like that, so E of S will be just equals to summating K equals to 1 to M. AK take out, we just replace this P of AK. Okay, we just simply define, it becomes like this. Then clear? So for simple random variable, very simple. We just take this. So that's why it depends on what is the probability measure. Then we can, if we know the probability measure, we can easily compute the expectation value for S. Okay, we always use this symbol mu to represent this expectation value. Okay. So next, this is quite straightforward. E1A equals to PA. I think this is quite clear. Just to verify this. 4.1.3. Okay, how to get part A? I think we can see what we can do is, so to get part A, so what we can do is, we can, let's say we write, so we can take S to be 1A with 1 plus 0 multiplied 1 complement. Okay. So that means we are taking A1 to be, A1 to be 1, A2 to be 0, and A1 to be A, and A2 to be its complement. Okay, we have this. So then we can see, this is actually I'm quite kind of stupid. So 1A can always be written in this way, right? So therefore, we can see E of 1 will be, we are talking about, so by the definition, we can take out 1, P of A plus 0 multiplying P of AC. Okay, so I am following this symbol. Okay, so I think it's clear. So this is actually just equals to A1 P A1 plus A2 P A2. Okay, so this is 0, so that's why the value for PAC do not affect. So and this is immediately you can get this is a PA. So this is how we get this equation. And the first one is even easiest because of we can always write 1 as 1 1x. Okay, so that means in this case I only have A1 is 1, A capital A1 is we are using omega. So then that's why we can directly get, so E of 1 will be P of omega, so that will be 1. So in fact, it should have a 1 multiplied P omega. Okay. So I think this is quite clear. If S is non-negative, so EX will be non-negative. Okay. It's my pen. So B is clear. So if S is greater than 0, then you can see A1, A2 up to AN must be also greater or equal to 0, okay, by the definitions. So hence you can see E of X is equals to, you are summating of A1 PA1 plus A2 PA2 until AM PAM. I think it's clear, so it cannot be negative, right? And then, so this is also quite straightforward. E of S plus T must be ES plus ET. If you put EAS must be AES. Okay, so I think it's clear. Right, so this is done. How we going to construct or we define the expectation value for non-negative random variable. Oh, sorry, the simple random variable, just like that. Okay. We just take this. So this is the easiest case. Okay. Okay, next we go to the non-negative random variables. Okay, so this will be slightly complicated. So we need to consider a more general case. Okay. Okay, in these sections, so only 4.2 only, okay, not for the remaining. So in this section, at least, we consider extended non-negative random variable x, meaning that we allow x to take value to infinity. Okay, the value of x could be up to infinity, unlike our previous sections. Okay, next, I think this is quite standard things. So we said that xk is a sequence of random variable converge up to x. That means x1 is an increasing random variable. x1 less equals to x2, x2 less equals to x3, and x will be equal to the limit of x. Okay, so we use this symbol. And xk converge to x increasingly. That is x1 greater or equal to x2 and greater or equal to x3, and x will be limit of xk. So in this case, so this is a notation. Okay, so this is for, I think, 4.2. So just to let you remark over here. So when we put xk going up to x, right? So this one actually means supremum of xk, okay, or limit of xk is equals to x. So these two are the same. This one or this is equals to x. So likewise, when we say xk decreasingly, converge to x decreasingly means the infimum of xk is equals to x. Okay, so take notes of this. So, okay, next will be this. You can take it for granted. Okay, maybe if x is a non-negative random variable, we can always construct a sequence of simple random variable xk and converge to x increasingly. So the proof, I'm not going to look at the proof, but just give you the construction for it. So this is one way that we can construct such a simple random variable. Okay, maybe I think it would be better I do it over here. So you don't, it doesn't really matter. You don't, just to let you know, we can have this. Anyway, forget it. If we have time, we come back later. Okay, maybe we come to this. So this is how we define it. So let's look at the, I think I just put it over here. Definitions, 4.2.2. Okay. So before we look at this definition, let's look at here. For simple random variable, the expectation value will be just given like that. So we can always compute the value explicitly using this formula. So it's very simple, okay, easy to calculate, right? Now we come to the next one, that is for non-negative x. It's a little bit complicated, so we can say like that. So for x greater or equals to 0, so what we can do is we just construct how to do it. First, we can that we construct simple random variable, a sequence of simple random S1, S2, S3, and so on, such that it fulfills these two conditions. This A, S1 less or equals to S2 and less or equals to S3, and so on. So that means it is increasing. Okay, so SK is increasing. It's an increasing sequence. And B, limit k to infinity for sk is equals to x. So in other words, so you can say x is equals to supremum of this. So you may forget about this supremum thing. Okay. So what we can do is first we construct simple increasing sequence of simple random variable that is increasing in such a way that the limit is equals to x. Okay, 1, 2, 3. Yeah. Simple random variable that is increasing, whose limits is equals to x. So if you have this, so then first we construct this sequence. Then what we can do is we just define e of x to be the limit of e of sk. Okay, so there's no specific formula for you to compute ex, but we just tell you we can follow this algorithm or this method to construct it. Okay, here, just to let you know, here, definitions 4.1.2. Okay, here e of sk is computed using definitions 4.1.2 because of this. All the sk are simple random variable, so that means we just using this formula to compute it. So that means we can actually compute the expectation value for all the sk, and then we take the limit for it, then that will be our ex. So this is how we define the expectation value for a non-negative random variable. Okay, so you might wondering whether, or you might wondering how to construct this kind of simple random variable. So yes, we can always construct such a random variables. Okay, so the answer is here. So the construction will be like this. Okay, so you need not study how this thing looks like, or you don't have to verify it, but just let you know, we can always construct such a sequence of simple random variable using this way. Okay, so if you are interested, you may verify. So what you can do it one by one. So you can take two running index. First of all, k will be a number. One begin from 1, yeah, 1 up to infinity, and m is a running number running from 0 up to k to k minus 1. So you can first we construct this event akm like this, okay, and we construct sk to be this. So if you are interested, you can check each sk is simple random. I think this is quite obvious. Okay, this thing must be simple because of here is a finite value. Okay, it's a linear combination of indicator functions. Okay, so therefore it must be a simple random variable, and it must be increasing. So you may verify it on yourself. Okay, and also the limit of sk will be equal to s. So I think part 2 and part 3 is quite challenging. So if you are interested, you may verify on yourself. Otherwise, you may accept it. Okay. Anyway, it's not important. I put it here just to let you know. We can always construct such an approximating sequence. Okay. So you don't have to worry about it. We can always have a way to construct it. Okay, next, I think this is quite straightforward by using the definitions here. If X and Y are non, I think something missing here. Okay, never mind. So I think it's okay. So I think this is quite straightforward. Expectation value is linear. Okay, you can see. And if X less or equals to Y, so EX will be less or equals to Y. Okay, I think this is quite straightforward by according to the definition. And the next one will be the Facto Lemma. Okay, so this is an important formula, so-called the Facto Lemma. We're going to apply this formula quite frequently in the following chapter. So I hope you remember this. Okay. So if we have a sequence of non-negative random variable xk, take note, I am using xk here, which means this x might not be simple. All right. Then E lim inferior of xk will be less with the limit inferior of E xk. Right, so this is the important formula. Maybe I will put it here. Find a way to, it's very simple, not difficult, okay, but find a way to memorize it. Okay. Facto Lemma, okay. Only one hypothesis, suppose X is only one hypothesis, X is greater than 0, then I'm going to have E of limit inferior of xk will be less or equals to limit inferior of E xk. Oh, okay, so this is xk. So forget about the next theorem. So let's look at this example first. So let's jump to this example 4.2.6 first, all right? Okay, part A. P of limit inferior of AK will be less or equals to limit inferior of P of AK. Okay, how to verify this? So we can actually prove this by using our Facto Lemma here. Okay, before this, so we need to recall some of the formula. So recall, I think the first one still fresh, we just discussed it. E of 1A is equals to P of A. Okay, so this is actually we have discussed just now, okay, in the first section. Okay, second, will be this. Okay, maybe I'll put it over here. The second one. So the indicator function of limit inferior of AK will be equal to limit inferior of 1 AK. You take notes of it. So this is applying to set. So whereas the limit inferior over here, so which is applies to values, okay, values, numbers. I think you can say numbers. So although I'm using a limit inferior, but two different kind of the formula, right? Okay, so I think using these two is good enough for us. Of course, together with this Facto Lemma formula, we are able to prove this. Okay, so let's look at the proof. So we can apply this. So what we can do is we take xk to be 1 AK. Okay, xk to be 1 AK. Just look at this formula. Then you look at here by Facto Lemma. We're going to have this. Okay, remember this formula. We have this E of limit inferior of xk less or equals to limit inferior of E of xk. So this is a Facto Lemma, the formula. Now we're putting this inside. So E of limit inferior of 1 AK. Okay, next will be this. Now we applying this formula here. Okay. E of 1A equals to PA. So we apply into this part. So then this will becomes P of AK. Okay, so we just applying this formula over here. Okay, so no problem. Okay, next one. Okay, so we are using this formula. So this one can be put it as E of. Actually, we just do the variation inside 1 limit inferior of AK. So this is applying this formula. Okay, how is it? Okay, not here. Maybe just to let you know. So which apply to these two. Yeah, apply here. So almost done already. So I'm using this once again. So this will be equals to P of lim 1 AK. So this. Right. So and applying this once again. So then we have this solved done. This is how we get the formulas over here. So not difficult, but we have to apply several formulas for several times. Okay. All right. Sorry, I think it's a good time to stop here now. Okay. Okay. Next lecture we will come back go back to this monotone convergence theorem, so which is actually equivalent to this Facto Lemma. Okay, so we shall look at the proof for this, how to use the Facto Lemma to prove this monotone convergence theorem. So it's a very good example to demonstrate how to apply this Facto Lemma and how to do these calculations. Okay. All right. Okay. So I think I should stop here now. Again, any questions?